Hey there, this is Mrs. Sharp, and we are going to go over 110 today. Even though I'm not here with you in person, I'm here with you in spirit in my disembodied voice. And I'm going to go through notes with you on the law of multiple proportions. So today I want you to be able to tell me what that law is and use it to predict the masses of elements in a compound. So here we go. I hope you are as excited as me. The law of multiple proportions. First of all, let's talk about what this applies to. You got to have two different compounds made up of atoms of the same types of elements. So two different compounds, meaning, they are very different things, but they're made up of the same combination of elements. So as an example here, water and hydrogen peroxide. So look at the formulas. Hydrogen and oxygen are the only two elements, but they are very different compounds because their formulas aren't the same. And you know water and hydrogen peroxide have really different properties too. Water is clear and colorless. It is very unreactive. Hydrogen peroxide is very reactive. Similarly, there's a cuprous chloride and a cupric chloride that both contain just copper and chlorine. But look at their formulas. They are different. Cuprous chloride is green, cupric chloride is blue. So even in color they're different. Another one that you may know of is carbon monoxide versus carbon dioxide. So that's what we're talking about here. Same elements in the compound, but two different compounds. So here's what it actually says. When different compounds are formed by a combination of the same elements, that's what we were just talking about, different masses of one element combine with the same relative mass of the other element in a ratio of small whole numbers. That sounds really, really complicated, but you could think of it like this. Here's element 1, element 2, compound 1. Element 1, element 2, compound 2. Element 1, element 2, compound 3. So if the mass of A stays the same, then the mass of B is going to differ by a ratio of a small whole number. It might not be 1 to 2 to 3. But it's going to be some small number. Here's what's important. Find what's the same first. With like my good circle. Find what's the same first. So like that A being the same throughout, figure that part out first. Here's an example problem. Looks like this on your slide. Get it all up there. A lot of information to sift through here. First thing you should know is that there is a typo. I don't know who did this slide. Okay, it was me. So it's two different compounds are made out of, should say lead and oxygen, not iron, because if you look down here, I've got lead in the compound, not iron. Here's the first compound, here's the second compound. The law should apply because I've got two different elements, but they're the same from compound 1 to compound 2. The only difference is that their formula is different, so that makes them different compounds. So it says if a sample of compound 1 contains 207.2 grams of lead, there will be 16 grams of oxygen. Fabulous. Let's write that down. So here's compound 1. I'm going to write it as a ratio. So I'm going to write 207.2 grams of PB, and then I'm going to set it up as a ratio for every 16.0 grams of oxygen. So if I have 207.2 grams of this, I should have 16 grams of this. Sample 2 contains 207.2 grams of lead. How many grams of oxygen will be in the sample? So look at, find what's the same first. The PB stays the same in terms of mass. Does the oxygen stay the same in terms of mass? No, it does not. It should change in a whole number ratio. That whole number ratio in this case is 2. because the amount of oxygen goes up 2 times from first to second. So if this goes up by 2, the mass of oxygen in that compound should be 32 grams. And remember, that's if you have 207.2 grams of Pb. All right, so there's example 1. Here's example 2. You'll find that this is kind of the same sort of idea. We're just working a little backwards in this example. Laughing gas is composed of nitrogen and oxygen only. When a sample of laughing gas is decomposed, remember that means to fall apart, 28 grams of nitrogen and 16 grams of oxygen are formed. Let's go ahead and write that down. So for laughing gas, we've got, I'll put laughing gas. We've got 28 grams of nitrogen for every 16 grams of oxygen. Nitrogen monoxide is it's capital N, capital O. When that's decomposed, I've got 14 grams of nitrogen for every 16 grams of oxygen. What is the formula of laughing gas? So we don't have a formula for laughing gas, but we know it has N and it has O in it. We just don't know what those two things are. So remember, find what's the same. In this case, mass of oxygen does not change. The ratio of nitrogen to oxygen does change. So here, where we had 14 for 16, here we have 28 for 16. So going from NO, nitrogen monoxide, to laughing gas, the amount of nitrogen in terms of mass goes up by 2. So that means the formula, the mass should go up by 2, and we reflect that here. So oxygen is the same. Nitrogen goes up by a factor of 2, a small whole number. So this is the formula of laughing gas. And yes, it's the same nitrous oxide that you use in cars. So, example 2. Last example is probably the most complicated example, the most difficult to wrap your brains around. So here's what I'm going to do. We're going to do one example today. You have one problem in your book assignment today that deals with this that you'll probably struggle with a little bit. Maybe not. I could be wrong. If you struggle with it, it's okay. Try to set it up exactly like we did here and see what happens, and we will go over it on Monday. But do try it, please. So let's go over this. It says 2 different compounds contain only copper and chlorine. Here are their percent by mass information, or their percent composition like we've been talking about this past week. Notice how they're different. So because they are different, we know that they are 2 different compounds. We want to know how the formulas of the 2 compounds differ from each other. We don't necessarily want to know their exact formula. We just want to know how they differ from each other. So I put some helpful hints on here. First, find the ratio of copper to chlorine in each compound by pretending you have 100 grams of the compound. If you have 100 grams, the percents can just become grams. So let's back up a little bit and do that. So if I assume I have 100 grams, then 64.20% is 64.20 grams. So if I'm going to find the ratio of this time I want you to set it up a little bit differently. I want us to do a ratio of copper to chlorine like this. So I'm going to take my 64.20 grams and I'm going to divide that, remember that's of copper, and I'm going to divide it by 35.80 grams, and that's of chlorine. Now, you may be thinking that you're lazy and I don't want to write grams of blah. Well, if you write grams of blah, that's really going to help you keep it straight in your head what the crap is going on. And if you put that in your calculator and actually divide 64.2 by 35.8, you get a ratio of 1.79 grams of copper for every 1 gram of chlorine. Because your answer is 1.79, which is the same as 1.79 divided by 1. So what does this say? For every 1 gram of chlorine, there's 1.79 grams of copper. Let's do the same thing down here. 47.27 grams of Cu, 52.73 grams of Cl. If I do that, so look how that ratio changes. Here I had 1.8 times as much copper. Here I don't have even as much copper. So the ratio changes dramatically. Okay, so what? What do I do with that? Remember, I want to know how these formulas differ. So the ratio changes by a small whole number. What is that small whole number? Well, I gave you another helpful hint. Let's go to that slide. Look how the ratios differ. It should be a small whole number. So take your compound 1 ratio from that and divide it by your compound 2 ratio. That should give you a small whole number. So that first ratio was 1.79. And remember, that was grams of copper, and it was for every 1 gram of chlorine. We're going to divide that by 0.9 grams of copper for every 1 gram of chlorine. Well, what this is going to do is it's going to get rid of pretty much everything except for these two numbers. So we're essentially dividing 1.79 by 0.90. Punch that in your calculator, you pretty much get 2 on the dot. So the ratio of copper to chlorine in compound 1 is twice as much as the ratio of copper to chlorine in compound 2. 2 times. So let's go back to those 2 compounds. All right, so we said that the ratio of copper to chlorine here is 2 times as much of the ratio of copper to chlorine here, or the mass. So that means that here, if I have this ratio, then the mass of the chlorine is twice as much, or is represented by a ratio of 2 here. Now, is this the real formulas? Maybe, maybe not. But what this is showing is a reflection of the copper and the chlorine ratio changing. And I know that that's weird. I know that that's hard to understand. But it makes sense looking at these 2 compounds. If the ratio from here to here we decided is differ by a factor of 2, that should be reflected here. So copper, 1 to 1 here, 1 to 2 here. Okay, so my chlorine is represented 2 times as much in this as in compound 1. So like I said, please just give it a try. I don't expect that you're going to understand it 100% the first time you go through that, but give it a try, and we'll talk about it on Monday. Please remember a couple of things. First of all, you took 1.7 today. 1.9 is going to be on Tuesday. The book assignment, some of those are ones that you were assigned yesterday, and I said don't worry about those. It's page 88. 19 through 23. But wait, there's more. There is some practice problems for these for these multiple proportion sorts of situations too. And I'm not remembering exactly what page that is on right now. But there's just one other problem. And you know what? I will write it on the board. That's the one I just want you to give a try. So, this is Mrs. Sharp signing off. Be good. Have an awesome weekend. And I will see you later. Bye-bye.